unloaded the on auxiliary track. You are able to see रैक खड़ा है आपका यहाँ पे और auxiliary track पे we should unloaded the portals on auxiliary track. You have also seen the safety aspect. You have seen one labor is comes just nearby the train. मैं वही पिक्चर लिया था और इसको सेफ्टी एस्पेक्ट को हमें बहुत ज्यादा देखना है कि अपोजिट साइड की ट्रेन की स्पीड हम क्या दें. यदि वो थोड़ा सा भी हटता तो रन ओवर हो जाता. यू आर एबल टू सी. आपको दिख रहा है? हेलो.
यस सर.
बिल्कुल मैंने लाइव पिक्चर लिया था. ये बिल्कुल ये इंसिडेंस हुआ था साइड पे. इट इज पोर्टल अनलोडेड ऑन द ऑक्सिलरी ट्रैक. It is 3 tier or 2 tier as per our requirement. We should loaded our BFR with 3 tier or 2 tier. First our new panel should be taken by our portal. You have able to see how the portal bar lifted the panel. There may be hindrance during transportation of panel. Then 3 tier panels should be unloaded at our site, and then port to existing track. It is every 12.6 meter we should cut the rail and put the our fish plate. Are you able to see?
Yes sir.
And first panel should be lifted by the portals from the existing track. These are the clamps how we can lift it our panels. It is our operator. Then we should lift it our first panel. And you have also seen the clear picture of what is the condition of ballast after lifting. You are able to see? Hello?
Yes sir. Yes sir.
And ballast should be regulated by manual means. इस तरीके से ballast को regulation करना होता है. It is after labor should be plane the ballast. There is also we will plan for the TRR work. You are able to see in the TRR work. In the behind our Pickers work there is 2 to 3 day before work we should also plan our TRR. Gracing of ERC. First panel should be unloaded at the side. We should maintain our gap. It is first panel should be unloaded. Gauge level should be taken, and we also take the marking before putting the first panel. There is any height difference. The height of the sleeper is 210 and height of the rail is 156. Then the reading, what is the reading? Either there is level difference or not before putting the panel. And it is a basically alignment rod. Basically we use the alignment rod. देखिए इस टाइप की एक रॉड बना के रखते हैं कि जो ऑक्सिलरी ट्रैक से हमारा अलाइनमेंट फिक्स अलाइनमेंट को बता सके और हम अलाइनमेंट पीछे पीछे लेते जाते हैं ब्लॉक एक्टिविटी में. We should make the alignment like that, and after that we should also old fish board plate we should collect. It is a piece of as per local arrangement we should make that type of piece. One side 60 kg rail, one side 52 kg rail, and one combination joint at center. These piece we should utilize when TRR is completed. आप सबको दिखाई दे रहा है ये टुकड़ा? हेलो?
यस सर.
इस टाइप का पीस को हम बना लेते हैं.
आप ऑफिस वाला काम
को क्या है बंदा, हाँ बेटा मैं पीरियड में हूँ, और आदमी को भेजा, थोड़ी देर में बताता है वो सामान का। अभी आया होगा
10:25 पर।
हाँ हाँ। अरे
और उनका त्रिपाठी जी का वो आया था बेचारे में रिटायरमेंट वाला, वो कर दिए थे।
नहीं, हेलो,
छुट्टी में थे ना।
जे 52-60 का एक टुकड़ा हम बना लेते हैं। देखिए इस टाइप से कट मशीन, अब यहाँ पे टीआरआर हो गया है, तो वन साइड 60 kg, वन साइड 52 kg, इट शुड बी पुट आफ्टर कट। आप लोगों को दिख रहा है?
हाँ सर दिख रहा है।
एंड रेल लेवल शुड बी चेक लाइक दैट कि हमारा जो एग्जिस्टिंग रेल लेवल और हमने जो डिजायर्ड रेल लेवल जो मार्क किया है वो अचीव हो रहा है कि नहीं हो रहा है। वी शुड चेक लाइक दैट। क्लियर हो रहे हैं सारी चीजें कि नहीं? हेलो हेलो,
हो रही है सर, हो रही है।
क्लियर है सर, क्लियर है,
क्लियर है सर।
गैस कटर इज वेरी इंपॉर्टेंट। देखिए इसमें यहाँ पे एक खूंटी आ गई, इस टाइप की कोई भी चीज आपको हिंड्रेंस पैदा कर सकती है, तो गैस कटर इज अवेलेबल देन यू शुड कट बाय गैस कटर। और मैं इसमें आपको जो फीचर्स बताने वाला हूँ कि लेवल क्रॉसिंग के पास हमें बहुत प्लानिंग करना पड़, आइदर लेवल क्रॉसिंग पैनल हम पहले से प्री फैब्रिकेट कर लें तो बिल्कुल एट प्रॉपर प्लेस हम उसको अनलोड करें, आइदर वी शुड 2 ramp bars given, first ramp at that side, first ramp at that side, and all panel, and it is a troublesome job for replacement of these sleeper holes. आपका क्लोजर भी पड़ा रहेगा, तो वो काफी क्रॉसिंग पे आपको बहुत प्रॉपर प्लानिंग करना है। तो मैं आपको पहले ही सब कुछ बता चुका हूं कि ट्रैफिक ब्लॉक विद पावर ब्लॉक आपको मिलना चाहिए। प्रोटेक्शन बहुत इंपॉर्टेंट है। देखिए कई रेलिंग साइड पे एक्सीडेंट हो चुके हैं, तो बोथ साइड का प्रोटेक्शन बहुत इंपॉर्टेंट है, और बोथ साइड प्रोटेक्शन करके ही हम, और इसमें डिस्चार्जर रॉड लगाना है प्रॉपर जंपरिंग करके, क्योंकि कई बार एटी होने मतलब एटी की भी अर्थिंग करना है, क्योंकि बहुत लंबे पैनल्स हो जाते हैं तो हमारे एटी में भी करंट आपको शॉक लग सकता है। इसके बाद सीक्वेंस 1 by 1 सफिशिएंट लेबर होना बहुत जरूरी है, क्योंकि फिलिंग ऑफ बैलास्ट, लिंकिंग ऑफ पैनल, पैकिंग ऑफ स्लीपर, टीआरआर यदि आपने प्लान किया है, बेल्डिंग आपने प्लान की है, तो इन सब एक्टिविटी के लिए प्रॉपर लेबर और सुपरवाइजर आपका होना चाहिए। इसमें हमेशा ध्यान रखें कि गैप्स ऑफ द जॉइंट रखना है और रेल टेम्परेचर के हिसाब से, और स्क्वायर एज ऑफ स्लीपर हमारी डिस्टर्ब नहीं होना चाहिए, पर्टिकुलर कर्व ट्रैक के ऊपर। एंड डे के जनरली जो गैप है और वो हम इस तरीके से प्लान करें कि, और लास्ट में रैंप बहुत इंपॉर्टेंट है कि 25 mm पर रेल लेन से ज्यादा का रैंप डाउन नहीं होना चाहिए, क्योंकि आपने यदि हाइट कर दिया 25 mm पर रेल लेन से ज्यादा का हाइट का डिफरेंस नहीं होना चाहिए। तो पार्टनर हमेशा कंटिन्यूअस बाज रखना है ऑक्सिलरी ट्रैक पे कि किसी कारण से पोर्टल्स की स्टेबिलिटी और कंटिन्यूटी फेल नहीं होना चाहिए। और आउटपुट हमें तभी मिलेगा कि क्वालिटी और क्वांटिटी दोनों जुडिशली हम रिव्यू करेंगे, और इसमें हमेशा ध्यान रखें कि लेवल क्रॉसिंग प्रॉपर प्लानिंग करें, नहीं तो देखिए इस टाइप से प्रॉब्लम आती है कि हमको यहाँ पे भी पैनल कट करके डालना पड़ रहा है, उधर पे भी हम इस तरीके से पैनल कट करके डालना पड़ रहा है, तो इस टाइप की प्रॉब्लम आती हैं, तो आप प्लीज यू शुड प्लान अकॉर्डिंगली। इसके बाद एफओबी और आरओबी के क्लियरेंस के हिसाब से, इलेक्ट्रिफाइड एक्सट्रक्चर के क्लियरेंस के हिसाब से सारी चीजों को प्लान करना है, और एडुकेट क्वांटिटी में बैलास्ट को रन डाउन करना है। सिंक्रोनाइज हम TRR कर सकते हैं, और फिर केबल्स का रेस्टोरेशन, OHE कनेक्शन का, PRM और टेम्पिंग मशीन प्रॉपरली रखना है, और SCJ को प्रॉपर जगह पे हमें वो देना है। और रैम डाउन में हमेशा ध्यान रखना है कि 25 mm पर रेल लेंथ से ज्यादा का रैम डाउन का लेवल डिफरेंस नहीं होना चाहिए। इसका हमेशा रैम डाउन को ध्यान रखना है। देखिए इस तरीके से रैम को हम करते हैं जेट से ओल्ड और न्यू स्लीपर के जो ट्रैक पे। और यदि फिर बाद में कोई यदि स्क्वायरिंग और स्पेसिंग स्लीपर की हमारी डिस्टर्ब हो गई तो हम उसको ठीक करेंगे, फुल फिटिंग्स को कंप्लीमेंट करेंगे, टेम्पिंग और स्टेबलाइजेशन ऑफ ट्रैक करेंगे, ट्रेनिंग आउट बैलास्ट करेंगे, लेफ्ट ओवर स्लीपर को करेंगे, डिसमेंटलिंग करेंगे और LWR में कन्वर्ट करेंगे। इट इज बेसिकली सेमी मैकेनाइज्ड सिस्टम है। इसमें 80 बनाना बहुत टीडियस जॉब है। आपकी दो फ्रंट पे, एक तो आपकी बेस डिपो एक्टिविटी, एक साइड की एक्टिविटी, और 2 बार ट्रैक रिंकिंग और रेल रिन्यूअल इसमें करना पड़ता है, इसलिए थोड़ा उतना अच्छा नहीं है। जनरली 260 मतलब 20 पैनल्स के लिए मैंने देखा है कि 2 घंटे का ब्लॉक करीब करीब सफिशिएंट होता है। मैं एक एक चीज पिक्चर दिखा के आपको एक एक चीज डिस्क्राइब करने की कोशिश करता हूँ, फिर मैं पावर पॉइंट पे लूंगा। आज 10 मिनट बचे हैं तो आज मैं पिक्चर से आपको TRT समझाने का प्रयास करता हूँ। बेसिकली इन TRT आप देख रहे होंगे कि हमें पैनल फैब्रिकेशन नहीं करना होता है। बेसिकली हम वी कैन लोडेड द स्लीपर इन नंबर ऑफ लेयर्स, और इसमें मैक्सिमम 21 स्लीपर एक लेयर में हो सकते हैं, और जनरली 19 स्लीपर रखते हैं। 19 स्लीपर शुड पुट द पोर्टल्स मूव ऑन आवर रैक, नीचे नहीं मूव होते हैं, रैक के ऊपर ही मूव होता है, आप इस पिक्चर में देख रहे होंगे। और बोथ साइड भी प्रोवाइड आवर इंजन, बेसिकली जनरली for sighting purpose and all other purpose you should provide engine on both side। आप इसमें पिक्चर में देख रहे होंगे। फॉर्मेशन ऑफ रैक सबको दिख रहा है सर। इट इज 3 टायर अरेंजमेंट, और स्पेसर इसमें देखिए रेल डाला है, रेल की जगह वुडन फीचर्स भी डाल सकते हैं। 1 लेयर मैक्सिमम 21 स्लीपर, बट वी ऑलवेज केप्ट 19 स्लीपर। सबको दिख रहा है?
हाँ सर।
हेलो,
हाँ दिख रहा है सर, दिख रहा है।
It is and 1 rail is provided and channel should be provided for supporting these sleepers। आप देख रहे हैं इस टाइप से स्पेशल बार इसमें डालना होता है, स्पेसिंग, क्योंकि वो जो पोर्टल्स के चैनल्स हैं ना वो यहाँ पे फिक्स होते हैं। मैं आपको पिक्चर में दिखाता हूँ। इट इज अ ब्रिज, बेसिकली इट कॉल्स ब्रिज की 2 वैगन को कनेक्ट करने के लिए इस टाइप का स्पेस होता है, ब्रिज अरेंजमेंट जिसे बोलते हैं। आपको
दिख रहा है R12
इस टाइप से ब्रिज अरेंजमेंट होता है। R11 R12 पर्टिकुलर फिक्स अरेंजमेंट होता है, उसको वहीं लगाना होता है, एक नंबरिंग रहती है उसमें, और वी शुड पुट एट प्रॉपर प्लेस। आप कहीं का भी कुछ भी नहीं लग सकते इस टाइप से। और इसमें दोनों पोर्टल्स दिख रहे होंगे आपको। आर यू एबल टू सी? 2 पोर्टल्स इज देयर, बेसिकली गैंट्रिक है, बेसिकली उसमें हम पोर्टल्स बोलते हैं। तो दे आर मूव्ड, एंड मैं आपको एक एक पिक्चर दिखाता हूं। देखिए इसमें आपको पिकर्स का एक्चुअल
ये बड़ा को थोड़ा मार दे, वो करखा मार दे बस।
You have seen the TRT real pictures. In that TRT we should make the 7 meter place by removing। हमें 11 स्लीपर निकालना होते हैं, क्योंकि जो बैलास्ट रेगुलेटर को अनलोड करना होता है वो करीब करीब 11 स्लीपर 7 मीटर्स का स्पेस हमें यहाँ पे मेक करना होता है। आप इसमें देख सकते हैं कि आफ्टर मेकिंग द स्पेसिंग वी शुड लिफ्ट इट अवर ट्रैक। आप इसमें देख रहे हैं कि ट्रैक को लिफ्ट कर लिया, हम 11 स्लीपर निकाल देंगे, देखिए इस तरीके से। एंड जो आगे आगे इस टाइप से प्लेट्स हम प्रोवाइड करते हैं, जो स्लेज है वो मूव होता है इस ट्रैक के ऊपर, और इस टाइप से प्लेट्स हम डालते जाते हैं। देखिए इसमें आपको पोर्टल्स को बिल्कुल क्लियर कट दिख रहा होगा। इसमें स्पेशल टाइप के व्हील होते हैं जो ऑक्सिलरी ट्रैक जो हमारे रैक पे ही मेड होता है उसके ऊपर मूव करते हैं। देखिए इसमें आपको स्लेज में दिखाने का प्रयास करता हूं। इट इज अ स्लेज, जो आप इसके पैर के पास देख रहे हैं स्लेज, अभी आगे की पिक्चर में भी दिखेगा, मैं आपको इसमें दिखा। इट इज स्लेज, इट मूव्स ऑन द ट्रैक। आप इसमें रेड रंग का जो रेड ऑक्साइड से पुता वाला देख रहे हैं स्लेज, सबको पिक्चर दिख रही है उसकी?
यस सर।
And it should be locked during initial setting. It should be locked कि वो पीछे ना चला जाए। आप इसको ट्रैक के ऊपर रख के it should be locked। और हम देखिए अभी क्लियर हो रहा है?
ये बोथ साइड लॉकिंग होती होगी ना?
और इस स्लेज के ऊपर ही हम अपनी जो कार को ला लेते हैं, पावर कार को, मतलब इसकी टीआरटी की पावर कार को ला लेते हैं और स्लेज के ऊपर आ जाती है वो। इस तरीके से 7 मीटर का स्पेस क्रिएट करते हैं। आपको इसमें बहुत क्लियर दिख रहा होगा, 7 मीटर का स्पेस क्रिएट किया हुआ है और अभी हम इसको ला रहे हैं। बेसिकली इट इज अ बैलास्ट रेगुलेटर। आप इसमें देख रहे हैं, मैं अभी इसमें करता हूं। इसमें आप इसको बैलास्ट रेगुलेटर को देख पा रहे होंगे। हेलो हेलो,
हाँ सर। यस सर।
बैलास्ट, इट इज अ बैलास्ट रेगुलेटर बेसिकली। और देखिए इसका जो हमारा गैंट्री होता है, इसका व्हील बहुत इस टाइप का, इसमें दांते होते हैं। तो कभी भी कोई भी जो इसका ऑक्सिलरी ट्रैक रखना है या कुछ भी नहीं रखना है, क्योंकि इससे बिल्कुल कट जाएगा। आपको देख रहे हैं एक मेजर एक्सीडेंट अभी बॉम्बे डिवीजन में हो चुका है, जिसमें कुछ लोग मर गए थे अभी टीआरटी मशीन्स पे, और इसलिए इसका मूवमेंट पे हमें बहुत ज्यादा ध्यान देना है। आप इसमें क्लियर हो रहा होगा?
अच्छा, उस आगे अपना फोन कर तो बैठ ले आने।
और देखिए स्लेज के ऊपर पावर कार आ रही है, आप इसमें देख सकते हैं। देखिए अभी एक पोजीशन पे आ गई, अभी मैं आगे बताता हूँ। दूसरी पोजीशन पे आई धीमे धीमे, थर्ड पोजीशन पे आई और अभी बिल्कुल एंड पे आ गई। आप इसमें देख पा रहे हैं सब लोग? हेलो,
दिख रहा।
देखिए इसमें स्लेज के ऊपर हमारे ये बेसिकली जो टीआरटी की पावर कार है वो इसमें आ जाती है। इसके नीचे प्लेट्स हम डाल के रखते हैं, सबको एक स्टील प्लेट दिख रही है, वो बेसिकली रेगुलेट करती हैं। और स्लेज में आप छोटे छोटे व्हील देख पा रहे हैं, अभी इसमें देखिए छोटे छोटे व्हील होते हैं। और आपका पहला स्लीपर उठने को तैयार है। इसके पीछे आपको बैलास्ट का खाली जगह है, जिसमें बैलास्ट, इसमें आपको नॉब दिख रही होगी, जो बैलास्ट का रेगुलेशन और कॉम्पैक्शन और स्प्रेडिंग पीछे पीछे करते हुए आता है। इट शुड बी ड्रॉप डाउन। देखिए स्लेज के ऊपर पावर कार पूरी तरह आ चुकी है। अभी देखिए पहला स्लीपर, इसमें आपको स्पेशल टाइप का हुक दिख रहा होगा, आर एबल टू सी। और देखिए बैलास्ट का रेगुलेटर भी जगह पे आ रहा है। हेलो, इसमें आपको हुक से पहला स्लीपर उठेगा। देखिए इसको पहला स्लीपर हम उठने को तैयार है। देखिए पहला स्लीपर उठाएंगे, देखिए आ गया बिल्कुल जगह पे। और इस तरीके से ट्रैक को हम बाहर कर देंगे। अब स्लेज के ऊपर पूरी की पूरी टीआरटी चलेगी। ट्रैक को बाहर करके इस तरीके से हम उठा के बाहर कर देंगे और वो ओल्ड ट्रैक से इसको कंबाइन कर देंगे। ओल्ड ट्रैक से इस तरीके से, इसमें स्पेशल टाइप के रोलर्स लगे होते हैं जो ट्रैक को, रेल को इस तरीके से पकड़ लेते हैं। वो लेटरली शिफ्ट भी कर सकते हैं। इट इज मूव लेटरली। और इस टाइप के प्लेट हम आगे आगे डालते जाते हैं, जिसके ऊपर स्लेज चलता है। इसको आप देख पा रहे होंगे। देखिए इस टाइप का स्पेशल टाइप का हुक रहता है इस मशीन में, जो कि रेल को लेटरली अपवर्ड, डाउनवर्ड और लेटरल तीनों तरीके से मूवमेंट करते हैं। तरीके से स्लीपर, न्यू स्लीपर की फीडिंग अपर साइड में होती है, ओल्ड स्लीपर नीचे साइड से हमारे जाते हैं। मैं आपको इसमें दिखाता हूँ। अपर साइड से इस तरीके से स्लीपर की फीडिंग होती है। मैं अभी आपको 3 टायर सिस्टम में स्लीपर नीचे आता है, फर्स्ट टायर, सेकंड टायर, थर्ड टायर और फिर गेट। इस तरीके से 3 टायर सिस्टम में स्लीपर नीचे आता है। और एक एक स्लीपर टीआरटी के द्वारा हम सीटीआर कर सकते हैं, मतलब कंप्लीट ट्रैक रिन्यूअल कर सकते हैं। TRR पर भी कर सकते हैं और TSR भी कर सकते हैं। इस तरीके से हम इसमें कर सकते हैं। आप इसमें देख सकते हैं कि 1 by 1 स्लीपर नीचे आ रहा है और हमने ओल्ड ट्रैक को इस तरीके से पकड़ा हुआ है। देखिए फर्स्ट स्लीपर शुड बी पुट डाउन। इसमें जो गेट होता है वो एक कैट कैम व्हील के द्वारा गाइड होता है। एक पर्टिकुलर डिस्टेंस पे ही खुलेगा वो। एक पर्टिकुलर मान लो आपने 60 की स्पेसिंग कर दी तो 60 के स्पेसिंग पे वो खुल के जगह पे आ जाएगा। और इसमें मैं दिखाने का प्रयास करता हूँ कि स्लीपर का अलाइनमेंट प्रॉपर बना रहे तो इस टाइप का अरेंजमेंट यहाँ पे रहता है TRT में। देखिए इस तरीके से TRT में अरेंजमेंट पूरा रहता है। स्लीपर बिल्कुल भी इधर उधर नहीं हो सकते, एक प्रॉपर प्लेस पे ही वो आते हैं। इस तरीके से 3 टायर अरेंजमेंट से वो नीचे आता है और ओल्ड ट्रैक को हम इस तरीके से ज्वाइन कर देते हैं। इसके पहले हम 7 मीटर का टुकड़ा रिमूव करते थे, अब आजकल हम टुकड़ा रिमूव नहीं करते हैं। इस तरीके से ओल्ड ट्रैक को हम ज्वाइन कर देते हैं और 1 by 1 हम इसको आगे लेते हैं। इसको देख सकते हैं प्लेट आगे आगे चलता जाता है, एक एक स्लीपर नीचे। देखिए इस तरीके से प्लेट को भी शिफ्ट कर देते हैं। स्लेट में इसमें व्हील लगे हुए हैं, वो धीमे धीमे आगे बढ़ता हुआ चला जाता है और एक एक स्लीपर इस तरीके से उठता जाता है और एक एक स्लीपर नीचे हम डालते जाते हैं। आफ्टर स्लीपर लेइंग होने के बाद हम रेल को जगह पे ला सकते हैं। वी शुड पुट द रेल एट साइड और उसमें हम कीज को लगा लेते हैं। देखिए इसमें रेल को हम जगह पे ला लेते हैं और कीज को हम फिट कर सकते हैं। देखिए अब इस तरीके से हम कीज को फिट कर सकते हैं। देखिए इस पिक्चर में आपको बिल्कुल क्लियर हो रहा होगा कि हम ट्रैक को किस तरीके से इस टाइप के जो हमारे अरेंजमेंट है हुकिंग अरेंजमेंट उनके द्वारा बाहर पे जगह जगह ला सकते हैं। और इस तरीके से रैक का फॉर्मेशन आपको दिख रहा होगा। बेसिकली अभी हर्स्को की मशीन थी यहाँ पे, हर्स्को की ट्रैक रिन्यूअल सिस्टम की मशीन। इसमें मैं आपको इसमें पिक्चर में भी दिखाता हूँ स्लेज का। देखिए इसमें आपको पिक्चर में दिख रहा होगा इट इज स्लेज। इसमें नीचे व्हील लगे हुए हैं जो कि ट्रैक के ऊपर चलता है, ये मेन पार्ट है इसका। और इट इज हुक जो स्लीपर को लिफ्ट करता है। मैं आपको एक एक चीज दिखा देता हूँ। मैं आपको पहले बताया कि ऑक्सिलरी ट्रैक इसमें व्हील में दांते होते हैं और इससे कहीं पे भी डेंजर होने की संभावना होती है।
These three formulas have been derived based on the rate of change of Kant, the rate of change of Kant efficiency, and Kant gradient. भाई माइक अगर खोल के रखोगे तो सबको डिस्टर्बेंस रहेगा। पराग मिस्टर पराग, आप देखिए जिसका माइक ऑन हो उसको बंद कर दिया करिए। Okay, so these three formulas are based on rate of change of Kant and rate of change of Kant efficiency and Kant gradient. The rate of change of Kant and rate of change of Kant efficiency is on comfort level, both in vertical and horizontal directions. When we talk about 0.008 CA into VM, this is comfort in vertical direction. When it is CD into VM, this is comfort in lateral direction. And we said that the rate of change of Kant or rate of change of Kant efficiency should normally be 35 millimeter per second. And in exceptional cases, it can be up to 55 millimeter per second. Accordingly, in exceptional cases, we say that this L1 can be 2/3 of L1, similarly 2/3 of L2, and 50% of L3. When we say 50% of L3, we are increasing the design twist from 1.4 mm per meter to 2.8 mm per meter. राजेंद्र सिंह, आपका मोबाइल आपका बार बार ऑन हो रहा है, आप इसको इंश्योर करिए कि आपका ये बार बार ऑन नहीं हो, पूरी क्लास डिस्टर्बेंस हो जाती है। ठीक है भाई मिस्टर राजेंद्र सिंह, आपका एक दो बार और होगा तो फिर मुझे आपको मजबूरी में बाहर करना पड़ेगा।
कर दिया सर, म्यूट कर दिया।
हाँ, okay, so this 35 millimeter per second and 55 millimeter per second, they are based on passenger comfort, and how they have been derived, you can see this RCD, rate of change of CD, will be what? CD upon time taken in transition. You know, if I consider a transition part of the curve, okay, let me just show you this transition part of the curve. So let me draw, this is transition length, okay, L. Now if the rate of change of cant, which I say, so this becomes your starting cant 0, and let us say this CA has been provided in a length of L. Similarly, when I talk about CD, the CD at point A is how much? Anybody? What is the CD at point A? Yes?
No, zero, sir, zero.
0. Very good. So CD at A equal to 0, and CD at B at this point, whatever CD we design, let us say 75 millimeter, 100 millimeter, or whatever you get, so that CD is at point B. Okay, so change in CD is how much? Say CD minus 0. Okay, so this is the change, and that change is taking in what length? That is taking place in length L. So if the velocity of a train is v, then time taken in transiting this transition length will be how much? V upon t. Simple. Okay, so when I say rate of change of CD, this is your time taken. This time is taken by train traveling at a speed of v, sorry, this is L. Okay, v by L. So v by L is your, or rather it is ulta, distance travel depend upon speed. Okay, let me just take another slide. So time taken here is L upon V. So time is L upon V, and change of CD is how much? CD minus 0, right? So when I say rate of change of CD, this simply becomes CD upon L by V. Okay, this L by V. This is rate of change of CD. Okay, now the CD which I have mentioned here, CD is given as G upon G, and this is delta P. G is your small g is acceleration due to gravity, and this delta P is unbalanced lateral acceleration. Okay, ULA, unbalanced lateral acceleration. This delta P, this can be derived. If somebody is interested, I will provide it in presentation slide, so that if somebody is interested, he can find out how this delta P and CD, they are related. Okay, now this ULA, I told you it varies from 0.2 to 0.4 meter per second square. But Indian Railways has taken this as 0.2. Okay. In exceptional cases, they have taken it as 0.3. So taken as 0.3. In exceptional case, normal case it is 0.2. And CD and delta P, they are related like this. Now you see this equation which we were discussing, that is this equation. So RCD here, RCD is nothing but CD minus 0.L by V. Okay, I hope you are able to see. So RCD is CD minus 0 upon L by V. Now CD is given as G upon G into delta P. Again divide by L by V as it is here given. Okay. Now this P upon L by V, delta P is equal, because rate of change of unbalanced lateral acceleration is taken as 0.2 to 0.3. So this delta P is taken as 0.3 meter per second square. And accordingly, if you substitute this delta P upon L by V value equal to 0.3 meter per second cube, that is in exceptional cases. Okay, that is in exceptional cases. Normally it is 0.2 meter per second cube. So, and capital G, you know, this is 1750. Small g is 9.81. And you get let us say the transition length required is say 150 meter, and to provide 150 meter the cost requirement is very high. Then it says you can go even up to 0.4 also. Okay, so when you take this 0.4 here, it becomes almost 70 millimeter per second. Okay, and the more it becomes, the requirement of transition length becomes less. So wherever transition length equal to as calculated by this formula, that is L1, L2, L3, or you provide by taking 2/3 of L1 and 2/3 of L2. I will not suggest take half of L3. Okay, take L3 as it is. But as you go on increasing the speed, the requirement of transition length, because this speed component here, that is going to govern the calculation for the speed. So if you take, let me just take my pen here. So if you increase the speed, the requirement of transition length goes up and up. Okay, so that way you can reduce 2/3 L. And for high speed, do not take half of L3. Take this as same as L2 CA, taking current gradient as 1 in 720. And then whichever comes maximum, that is L1, L2, L3, that should be selected as your transition length for higher speed. Somebody, in fact, people in the field mistake when they calculate requirement of transition length, say for 130 kmph or 160, they make 2/3 of L1, 2/3 of L2. Up to that point, it is correct. They also reduce L3 by half. That is wrong, because by reducing L3 by half, what you are doing, you are increasing design twist. So the margin available, maintenance margin available in case of twist parameter will be very less, and there will be some safety repercussions. But just reducing 2/3 of L1, 2/3 of L2, you are not bypassing any safety parameter, just you are slightly increasing discomfort to the passenger, and that too only up to 0.3 meter per second cube, whereas you can go in emergency in exceptional case even up to 0.4 as Americans are doing. So this point you must make very clear while calculating transition length for higher speed. Make use of this 2/3 of L1, 2/3 of L2, but please do not make use of half of. Speeds are less, but transitions are not available. That means transition length is not available. You are trying to, let us say, design a curve for a speed of 100 kmph or so, where even for 100 kmph transition lengths are not available. In that case, you can reduce this L3 by half. But when you go for high speed, do not reduce this L3 by half. This is my suggestion. Okay, though PV manual permits you doing this, or all L1, L2, L3, but for high speed, the maintenance margin available for twist parameter goes down. So that is not suggested. Okay. Now you must have come across a term called virtual transition. Virtual transitions, they are considered for providing cant to the extent it can be provided, okay, in a length equal to 14.785, and that is called virtual transition. Why? Because when a vehicle negotiates from straight to curve, the bogies, they gradually travel from straight to curve portion in such a way that the one part is on curve and one part is on straight. So the maximum bogie length has been considered as virtual transition, and manual permits that you can provide the cant gradient or cant, actual cant, in this length of virtual transition. Okay, and accordingly for mg 13.7 meter, and maximum cant that can be provided with cant gradient of 1 in 360 equal to 40 mm.
Sir,
Yes.
can it be called as a minimum transition?
Can it be called as a
Minimum transition?
minimum transition? Yes, you can call it a minimum transition, but it is not practically available on ground. You are not having practically availability of this transition on ground. Why? Because you simply jump from straight. As far as cant is considered, cant you are providing gradually from 0 to 40 mm. But curvature you are not providing gradually. Curvature, it is a sudden change from straight directly to curve.
Okay, sir.
Okay.
Thank you. Thank you, sir. Thank you.
Okay. So this is 40 mm that is possible. Here you can provide cant gradually to 40 mm, but change of curvature is sudden from straight to curve. Now coming to reverse and compound curve. Okay, reverse and compound curve, they are same what we have studied so far with certain additional features. So we will see those additional features. Reverse curve, meaning you have two legs of the curve which are in opposite directions. That is why its name is reverse curve. Okay, two legs of the curve which are in opposite direction, that becomes a reverse curve. Okay, and compound curve means it is a combination of 1, 2, 3, 4, any number of curves. So when you have combination of more than one curve, that becomes compound curve. Now see, curve is a curve with having same parameter, that is radius, degree of curvature, transition, super elevation, cant access, cant efficiency, everything is same. Only thing is, when you have two curves which are having their orientation in different directions, then it is a reverse curve, and accordingly compound curve. More than one curve in continuation is a compound curve. Now let us reverse curve. You see, it is a combination of two curves which are in opposite direction. Okay, you can see in picture. Now when two legs are joining which are in opposite direction, the common point, that is where two curves are meeting together, from this common point, the orientation of curve is in opposite direction. So the length of transition for this common point area, okay, length of total transition for this common point area is given as L1 equal to 0.008 CA1 plus CA2 into VM. Similarly, L2 008 CD1 plus CD2 into VM, and similarly L3. Other two ends of these two curves are designed on a similar way as for the simple curve. Okay. In between, that is the is given like this, or simply you can say L1 for first curve when added with L1. Okay, similarly L2 of first curve plus L2 dash of second curve at, I'm talking about at common point, so that becomes total transition length at common point. Okay, so that is the only difference. Now there are certain provisions given in PWM manual. Okay, we will see. This is that provision. It says for high speeds in group A and B routes, a straight of 50 meter length, okay, the common point area, okay, where two curves are meeting together. It says for high speeds in group A and B routes, a straight of 50 meter length shall be kept between two transition length, and if somebody is not able to provide this 50 meter straight between two legs of the curve, then increase the transition length to eliminate the straight. That means the portion in between two legs of the curve will be transition curve, and if that is not possible, then impose a speed restriction of 130 kmph. So that is the provision, and this requirement of 50 kmph, 50 meter, is only on consideration of oscillations at higher speed. You know, all trains running and track, they get induced vibrations because of effects. Now at higher speed, if this length is less than 50 meter, then chances are there that the induced frequency, induced vibrations in vehicle, they may match with the natural frequency of the vehicle, resulting into resonance. So to avoid resonance, either we should have complete transition or we should have a straight between two legs of the curve which is more than 50 meter. So that is the concept. Okay, now somebody asked me a question yesterday.
Excuse me, sir.
Regarding reverse curve. Yes.
Excuse me, sir.
Yes, please.
Sir, actually, even we could not able to give even a single meter in a reverse curve in our section. You can
which was
just one
please repeat,
even
please repeat
not
again.
it is audible, sir.
Yes, now it is audible.
Sir, actually, we could not able to give even a single meter as a state in our suburban and Bombay section. Completely just reverse curve totally. Yesterday also actually during design also we are getting problem for that. We could because
Yes.
while designing also we should get a zero sign at the junction of that. That is also we are not getting, and we don't have the street length also. So this causing a
See,
big problem for us for the day-to-day maintenance also.
If you measure a Versign at station +1, okay, let us say this is measurement at station number Versign, and this comes as, let us say, +5 millimeter.
Yeah.
Just I am taking one example. Okay. And when you take measurement of Versign from 0 station to -2 station at station number 1, if this comes as -5 millimeter, -5 because they are in a opposite direction. Okay, situation, then only you will get 0 Versign at common point, that is 0 station.
Okay.
Otherwise, if Versigns are differing here, then you will not get 0 station, and you can have this 5 mm this side and -5 mm this other side only when these two legs of transition curve, this side and this side, they are perfectly maintained, having same parameters. Same parameters means, yes.
इसमें what I meant to say, just suppose if you are not getting the same this thing, and if you are not getting it with 0 in the junction point,
Yes.
then what next? Because during design, because we are
No, nothing
design
next.
and not
Nothing. See, nothing.
sir.
Nothing to worry, because this is what I am telling to be perfect. But in maintenance, it is not always perfect. Okay,
Sir.
you are allowed to have some variation. You are allowed to have certain variation. So here, with what I am trying to tell is, when it is perfect, then only you will get this as 0.
Okay. Okay.
Otherwise, you are permitted to have those maintenance limits depending on the speed which you have designed for this curve. Okay.
Okay.
So nothing to worry about not getting 0 Versign at common point. 0 Versign at common point you will get only when you have these two legs perfectly maintained and perfectly designed. That is the ideal condition. And ideal conditions, of course, it is a desirable, but not necessary that you always maintain that ideal condition. Okay. It is a desirable condition, and no speed restriction, no worry about safety unless you are within the permitted range of change or permitted range of Versign variation, etc.
If you want to bring zero, if you want to bring zero, so
Yes.
whether we shall have to go for the again when once we design, and we will get the different legs of the junction. Okay, and if you want to bring the zero, then we'll have to redo the after putting the section point of view. This is the then what will be the
See, if you want to get it 0,
sir.
I told you this leg, that is, let me call this as a leg C,
Sir,
and under this leg as a D. So you should have,
if you want to bring the same this thing and during design after this thing and all, how we could be able to do that when it is possible?
yes, it is possible.
We
It
can
is
bring
possible. It is always possible.
we can bring both the legs equal during design.
Yes, that can be done.
So we have tried it. We actually, I will,
Tell me,
if you
first
permit, I
tell
will
me,
share you complete one case to you. After this, I don't want to wait the much time of others. Sir.
Mr. Chandrasekhar,
Sir.
please tell me whether these two flags are having same radius of curvature.
No.
They are having different radius of curvature.
Sir.
Okay. They are having different radius. So you will not get 0 in that case. Okay.
Sir.
And getting 0 is not a requirement also. Getting 0 here is not a requirement also. You know, let me take another sheet, and now I consider two different radius. Okay, this is one, and another is this one. Okay, so this is your common point, right?
Right.
Now this is minus 1, this is minus 1, minus 2, plus. Okay, similarly minus 2, minus 3. As I told you, when you have versine at minus 1 and plus 1 station same, then only you will have the 0 versine at this station. Let me call this station as A or 0 station. So when you have versine at and minus same, then only you will have 0 versine at station A. Now, because these are of radius R1 and R2,
Sir.
naturally the versine at plus 1, plus 2, plus 3, etc. stations will be different as compared to versine at minus 1, minus 2, minus 3, because they are of different radius. Now, when versine at plus 1 and minus 1, they are differing, you cannot have 0 versine at 0 station. Theoretically and practically both. Now you can ask one question. Let us say I have all design versine on this curve, that is leg number 2 and leg number 1. Let us say I have all design versine, perfectly laid design versines on leg 2. They are perfectly made. Similarly, on curve number or leg number 1, all versines, they are perfect at 0 station. Okay, and that can be very well calculated also.
Sir.
You will not have, because you are stretching your chord. Now let me draw it in such a way. Let us say this is my common point. Okay, I have on minus side, this is my minus 1 station, and another side I have plus 1 station. This is plus 1 station. Okay, and this side my versine is, let us say this is just example 10 mm. Okay, and this side it is on opposite side, let us say this is 15 mm on other side. Okay, now if it was plus 10 mm minus 10 mm, instead of plus 10 mm only plus 10 mm, then if you join, then the versine at 0 station will be 0. Now, but you are not having plus 10 because the radius is different. You are having plus 15 here. So when you join this, it will not be 0. It will be, say, plus 2 or minus 2. That will depend on your actual values and proper calculation. So in such a case, you will not get 0 versine at 0 station. That means the design versine at 0 station will not be 0. Rather, it will be either plus 2 or minus 2, depending on the design versine at station number plus 1 and design versine at station number minus 1. Para 4059B, same thing. How it reads, you can just go on. For high speeds in group A and B routes, a straight with a minimum length of 50 meters shall be kept between two transitions of reverse curve. On group A and B routes, on a straight less than 50 meters between reverse curves should be eliminated by suitably extending the transition length, that is making transition length straight to be 0. in doing so, it should be ensured that the rate of change of Kant and ensured that the rate of change of Kant and Versine along the two transitions so extended is kept same. This is important. You should not forget this aspect also. What it says, rate of change of Kant and rate of change of Versine along the two transitions so extended is kept same. Now while designing, while extending, it says if this 50 meter is not available, let us say it is only 30 meter or 25 meter or 40 meter, then transition length can be extended from both the sides. Let us say if it is 40 meter, then 20 meter extension from left side, 20 meter extension from right side. And in this extended portion of transition length, the rate of change of Kant and rate of change of Versine should be same. This is important. This you should keep a guard on it. Okay. And last is do so, then a speed restriction of 130 kmph is to be imposed. And this consideration is only on account of induced vibrations in vehicle matching with natural frequency of vehicle resulting into resonance. To avoid that, this provision has been incorporated. Okay, so that is all about reverse curve. That is all about reverse curve. Other features are exactly same as your normal simple curve. Then comes compound curve. Again, compound curve, as we discussed, it is a combination of more than one curve, and where it is joining that special care is in such case the transition length at junction area is given as L1, L2, L3, CA1 minus CA2. Rest is same. Okay, here because the difference between orientation is same. Compound means orientation of different legs is same. So the change in Kant from one curve to the other curve, that difference is counted here, and accordingly at junction the transition lengths are calculated by L1, L2 and L3. And it says if length is so calculated, that is the difference between one curve Kant and the other curve Kant is less, and the length of transition so calculated comes out to be less than 14.785, then you should design this junction area similar to virtual transition length. This is what it says. If length is coming less than virtual transition length, then common transition is deleted and the Kant is run out on the length of virtual transition. Okay, this is what it means. Now, some concept of vertical curve. Do we need to provide transition in anybody? Do we need to provide transition in vertical curve?
No, sir.
We do need vertical curve because in vertical curve there is no provision of Kant. Number one. Number two, we provide vertical curves only when the change of radius is large. Even for introduction of gradual change of Versine transitions are not required because Versines are very less. In case of vertical curves, transition lengths, etc. is not required. Kant is not provided, Kant is not required, and radius being large, the Versine is less. So there also change of Versine, gradual change of Versine, etc. is not required. Okay. Now regarding vertical curves, it can be a summit curve, it can be a sag curve. You can see if the change of grade is like this, first part or second part, then it is summit curve. Similarly, sag curve, the change of grade. So it will depend on how the change of grade is taking place, and accordingly it will be a summit or sag curve. And we provide vertical curve only when the algebraic difference between the grade is more than or equal to 0.4%. Okay, so this is the provision. If change of grade is equal to or more than 0.4%, then we provide vertical curve. And normally the vertical curve should not be provided in point and crossing zone area, unballasted diagonal bridges area, and transition portion of horizontal curves. And you can see the radius, minimum radius is this much, 4,000 in group A, B it is 3,000. So radius here it is much more. Okay, group A you can see more than 3,500, and there is some mention that if radius is more than 3,500, transition for the purpose of introduction of gradual change of curvature is not required. Okay, so here in this case group A route it is 4,000. So normally transitions are not provided in vertical curves. Now coming to speed on curve. How speed on curve is calculated? This is a very simple formula as given in IRPWM. I hope all of you must be knowing. V equal to 0.27 RCA plus CD, square root RCA plus CD. This is a very famous formula, and it is calculated based on basic fundamental principles of what we saw: super elevation matching with your speed, etc. And when we add for CD also, so it is derived from that same equation, V equal to 0.7 square root R CA plus CD. Okay, I will not go into the derivation part of it. But this is for circular part of the curve. Okay, circular part of the curve. Now, you can question, what does it mean, circular part of the curve? Because we have transitions also on either side, and transition length, etc. is related with the speed. You know, L1, L2, etc. So L1 equal to 0.008 CD into VM, L2 equal to 0.008 CD into CA into VM. So that part, if transition length is less, then there will be restriction on speed on account of less transition. So now I form it into two groups: speed in transition part, speed in circular part. Now, if speed in transition part is less because of inadequate transition length, naturally out of the two, you will have the least possible speed for this curve. So we design our transition and circular part of the curve in such a way that at no point of time the speed potential becomes less. I want my speed potential to be maximum. Okay. Now, wherever adequate transitions length are available, I not bother about the speed on transition length. I can straightforward go to this equation, that is 0.27 square root RCA plus CD. But if transition length are inadequate, then I must go for optimum solution. Optimum solution means speed in transition should be equal to speed in circular part of the curve. So speed in transition, please remember this, speed in transition should be equal to speed in circular part of the curve. This is very necessary to keep it in mind, because when we are going to study further, when calculating the speed, especially when turnout is taking off from transition part of the curve, when turnout is taking off from transition part of the curve, then in field you have lot many restrictions on this account, and somebody has on similar situation, on similar condition, Somebody has imposed a speed restriction of 45, somebody 75, somebody 65. So all that. Now, what exactly should be my optimum speed? That can be worked out by equating the speed in transition with, we will see this. Okay, let us first see this. A speed on curve having turnout, that means turnout taking off from simple circular curve, not on transition. So let us first see this, how it is to be calculated. Now my turnout can be a similar flexure, my turnout can be a contrary flexure. I hope you all know similar flexure turnout and contrary flexure turnout. Okay, now similar turnout, first case, how the resultant radius is calculated. I hope you must be knowing resultant radius in case of similar flexure, the 2 degree of curvature added here. Okay, the 2 degree of curvatures are added here in case of similar flexure, and then you get the resultant radius of curvature from resultant degree of curvature. How? Simple, degree related to radius by r equal to 1750 upon d. I hope you all know this. Radius equal to 1750 upon d, and d in case of similar flexure for this resultant, simply you add the 2 degree. 2 degree means degree of mainline curvature and degree of your turnout lead radius curve. Okay, so this is how first the resultant degree of curvature or resultant radius of turnout is calculated, and then first see equilibrium turnout. I am here calculating the speed for main line when turnout is taking off from circular part of the curve. This we are studying, and here in this case, first see equilibrium, that means cant required for train movement on turnout side is calculated by simply GV square. Here VT is speed on turnout. It may be 30 kmph, it may be 50 kmph. So GVT square upon 127. This RTO is resultant radius of lead curve. Okay, resultant lead radius curve. So you calculate cant equilibrium for turnout first, and on main line, how much cant now can be provided? If cant required on turnout is CEQ, then how much cant you can provide on main line? Anybody?
75 में
75 में से minus नहीं करना है. You have to add 75 because in this case on similar flexure,
Sir, it is 60 days, 60 days, 60 days.
Not 65. See, in this case of similar flexure, both mainline and turnout are oriented on same side. So cant provided on mainline becomes cant on loop line. And loop line, since cant required is only this much, maximum over and above it you can provide having limit on cant axis of 75. That means on main line, the cant can be provided equal to this plus 75. Because whatever you provide on main line, the same cant becomes provided for loop line. You not have cant axis more than 75. Okay, so on main line, the cant actual which can be provided will be CEQTO, so calculated for turnout side, plus 75. And with this CA, so calculated for main line, the speed then will be based on whatever CA you have been possible, it has been possible to provide on main line, plus CD equal to GV square upon 127 or main line, or simply speed equal to 0.27 you have calculated plus CD, which is permitted. Either it may be 75 or 100. So this is the simple method of calculating speed on turnout when it is taking off from similar flexure side and it is taking off from simple circular curve, not on transition. Okay. Similarly, when it is contrary flexure, again the process is same. We calculate cant required for turnout side by same formula, that is GV square upon 127 R2. Here it is GV square, not GV2. GV square upon 127 RTO. RTO is the resultant radius. Now, in this arrangement, that they are in two different orientations. So the cant provided on main line becomes negative cant for the turnout, and when it is negative, maximally simply the cant deficiency allowed in turnout side minus C EQ for turnout, which you have calculated. Actually can be provided on main line will be simply this cant deficiency, which may be 75, which may be 100 also. If somebody says I will take this as 100, then naturally CA to be provided on main line can be increased. So this CA is 75, that is cant deficiency minus CEQ, which you have calculated here for trains running on turnout with speed V, whatever speed, maybe 30 kmph, maybe 50 kmph. Okay, and this with this CA, then you calculate the speed with the same formula, that is CA plus CD equal to GV square upon 127 RM. Okay, this is how the speed is calculated on main line when turnout is taking off from circular part of the curve. Now, next is when turnout takes off from transition part of the curve. Okay, so we will have a break of 5 minutes and then I take up speed of main line when turnout is taking off from transition part of the curve. This point A1 is TPTC. Okay, this point A1 is just beginning of transition. And A, this is point A, where turnout is taking off. And the distance between A and A1 is either 20 meter or less. What I mean to say is you have no transition length left for providing gradual change of cant or gradual change of cant is starting from A. Now we saw that 20 meter this side and 20 meter beyond crossing change of cant is not permitted. Okay, so from A1 onwards, and if this crossing is located in B portion, let me say B to C is another 20 meter. Okay, this is 20 meter. So right from A1 and up to C, from A1, this entire zone, you cannot have change of cant. And I'm calling this zone as a turnout zone. Okay, I'm calling this as a turnout zone. But still you have some transition length available, that is from C to D, this part. This part is still some transition is available. And you may have zero transition also. That means leftover parts CD may be 0 or it may be some length. So here I am assuming that L1 is my out zone, because it is this turnout is taking off from initial point of starting point of my transition curve. So L1 is turnout zone and remaining length is L2, which may be another thing. This may be, let's say 0 to any value. Situation, after following the provisions of IRPWM, the possible cant which I can provide is only in this length from C to D. Okay, I can provide cant only in this portion, that is C to D. And whatever cant is provided will be continued in an entire transition part of the curve, and speed will be calculated based on this cant only. Please remember, speed of mainline curve will be calculated based on this cant only. Right? And here, as you can see, L1 and L2, L2 is certain value, non-zero value. Okay, it is not zero, it is non-zero value. Now, as I told you, in such situation, when we have inadequate transition length, the speed is to be calculated on line by which means speed in transition part of the curve and speed in circular part of the curve. They both are equated together. Okay, they are both equated together. So accordingly, here it has been done. As you can see, rate of change of current efficiency I have taken as 55 millimeter per second into L2 upon CA. This 3.6 is simply a conversion factor converting to meter per second. Okay, and this is equal to 0.27 or CA plus CD. Here CD has been made equal to CA for getting optimum solution. Now with this, you the CA which can be provided in such situation. Okay, please just look at it. L2 is a known parameter which is available. 55 mm, that means I have already taken the maximum value of rate of change of current efficiency, okay, which is equal to 2/3 of your L transition length. So that I have already incorporated here. I have taken 55. L2 is known. 3.6 is simply conversion factor. I need to calculate the CA. R is known. So I calculate CA which can be provided. Now in field, what people are having doubt is that they think that in this available length of L2, let us provide a cant gradient of 1 in 360. And with that cant gradient, whatever CA they get, they take that CA as provided CA for mainline, and accordingly thereafter they calculate the speed of mainline curve, which is 100% wrong. Okay, it should not be done in that way. Of course, sometimes it may so happen that this method of calculation may not violate other provisions of rate of change of current efficiency or rate of change of current, but especially for higher speed, it is possible that in 95% cases, if you go as per cant gradient of 1 in 360, etc., it may result into violation. So instead of following that method, please see this, which I have done here. That is by calculating your CA from this formula, and the calculated CA should be less than CG plus 75. CG, what is CG? Cant required for good strain. Cant required for good strain is what? VG square upon 127. R, that is the cant required for goods, because goods train are running at slower speed. So goods strain, a cant required for goods strain plus 75 cant access, that value, okay, So this CA, whatever we have calculated as per the previous slide, should not exceed this CG plus 75. And also one more thing, if CA so calculated becomes more than 100 millimeter, because L2 is just a number. I have not mentioned what is L2. L2 may be sometimes 50 meters, L2 sometimes may be 100 meter also. So with 100 millimeter, if CA so calculated becomes more than 100 millimeter, meaning CD also becomes more than 100 millimeter because you have equated CA to be CD. But in that case, CA can be taken as more than 100 millimeter, but CD should be taken only equal to 100 millimeter, because CD maximum permitted with PC is only 100 millimeter. So in that case, CD should be taken only as 100 millimeter, CA whatever you calculate, but CA should be not more than this, CG plus 75, and CD in that case 100. So this is how you should calculate the speed of mainline curve when turnout is taking off from beginning of transition. Similarly, if turnout is taking off from end of transition, you see that this Gantt diagram and Versine diagram of this case will be, this is your Gantt diagram, okay, and this is your Versine diagram. Introduction of Versine is right from beginning of transition. So Versine gradually changes, goes up to maximum value at start of circular curve, whereas Gantt starts only from point C, 0 to D. Okay. Now next is turnout in between transition. So as you can see in my screen here, this turnout zone is L2. I have taken ATS to 20 meter this side, crossing to 20 meter that side, and that length I have termed as turnout zone. Now you can provide first Gantt here, that is L1, second Gantt here, because L3 is also available for providing Gantt. Okay, L3 is also available for providing change of Gantt, but in length of L2 you cannot provide any change of Gantt. Now how to go about for the calculation? Again, speed on main line, that is in this portion, whatever speed you try to maintain, the same speed should be in portion number 1 and portion number 2, and also in portion number 3. So same speed, you cannot have 3 different speeds, okay, in L1, L2, L3. So again, I use this optimum solution, and optimum solution, first I consider this L1 part. Again, same 55 L1 3.6 conversion factor CA1 equal to this. Similarly, second part, that is for L3, last part. And with this first item, I calculate CA1, then this CA2, and finally combining the two, I get the speed potential for main line in such cases, which is equal to 0.27 square root R CA1 plus CA2 plus CD1 plus CD2. Again, this is subjected to my CA should not be, that is total CA should not be more than CG plus 75, Gantt for good strain plus 75, and whatever CA1 plus CA2, which is equal to CD1 plus CD2, which I have taken, should not exceed more than 100 mm, as I have limited my Gantt efficiency to only 100 mm. That means this CD1 plus CD2 here, both put together should not exceed 100 mm. If by calculation it is more than 100 mm, only. This is how the speed is to be calculated on mainline when turnout is taking off from mid part of your transition curve. Similarly, when you take third case, that is turnout taking off from end of the transition part of the curve, same concept. Now you have this L1 length available for providing Gantt. This L2 is your turnout zone where you cannot have change of Gantt. So whatever maximum Gantt you can provide, that is provided only in L1. Again, I repeat, in L1, you should not provide this cant by simply cant gradient. No, concept of cant gradient should not be applied here. Of course, when you calculate this cant, you can check whether my cant gradient is exceeding beyond 1 in 360. If it is so, you must limit it. So finally, after considering all three cases, whether case 1, case 2 or case 3, the cant so being provided should be provided within the cant gradient also. That is a check for all three cases. Okay, the concept here is same. Use this formula, get CA equal to CD, finally calculate speed. CA so provided should be less than CG plus cant axis, and CD should be limited to 100 millimeter, and finally the cant gradient should be checked. So this is how the speed of main line is to be calculated when turnout is taking off from transition part of the curve.